Check this out. We've got something really fun today. This is so amazing, math. Oh man, again? 1.2, the limit of a function. We want to find the following limits from the graph of g of x. A limit is, as x gets infinitely close to the limit's value from both sides, that would mean from the left side and coming from the right side, what value does the function approach? First one is the limit of g of x as x approaches 0. So here is x equals 0, and we want to approach it from the left and also approach it from the right. What value does the function get closer and closer to? We can see that the function gets closer and closer to -1, and it actually equals -1 here in this case. But we don't care at the exact point, it's just getting closer and closer. So this one is -1. The limit as x approaches 1. So here's x equals 1, and we want to approach it from the left and from the right. Now you can see that we're going two different directions. From the left, if we try to approach x equals 1, we're going to head towards -infinity, and from this side, positive infinity. So this limit does not exist because it doesn't approach a specific value. Now this is a lot of writing for us in math, so we're just going to write in capital letters DNE. Next one, the limit of g of x as x approaches 2. So there it is, 2. We're going to approach it from the left, and we're going to approach it from the right. It gets closer and closer to 1. So that limit exists. The limit of g of x as x approaches 3. Now you can see on the graph there is a hole here, or a point of discontinuity. So if we try to approach this from the left and from the right, it's actually okay. We get closer and closer to 1/2. And even though the graph doesn't exist there, it doesn't matter, because the limit is what value does the function approach as you get infinitely close to it. Same with the next one here, the limit of g of x as x approaches infinity. So as we go off here forever, what value does this get closer and closer to? We know that it gets closer and closer to its horizontal asymptote, which is 0. Now, just for fun, and to check this value here that we had to guess, let's find the equation of g of x. We see that there is a vertical asymptote here at x equals 1, so that means we have a factor in the denominator that is unmatched. We also have a removable point of discontinuity here. That means that it's a factor in the numerator and the denominator with a root of 3. So putting those things together, our equation is like this. And you can see that if we cancel out this removable point of discontinuity, we put in the value of 3 here, we do in fact get the value of 1/2. In general, this is how we write limit. We say it like this, the limit of f of x as x approaches a, and if it has a limiting value, it will be L here. I highly recommend writing this in cursive so that you don't get mixed up and this doesn't start looking like a 1. We need to consider both sides coming from both sides, but we don't actually need to equal a, so that could be, like we saw before, a point of discontinuity. Find the limits of the following functions, this time from their equation. Now, if you can actually put in the value, if you can let x go to -3, then the question will be very easy. So in this question, we'll let x go to -3 because there's nothing preventing it, no non-permissible values. And then we'll just calculate what this is. So -3 squared is 9. Minus 3 is 6. So the value of the limiting value is 6, and also the value of this actual equation here is also 6. Now you notice that once I let x go to this limiting value, I don't need to write lim anymore. I've used it up, so to say. Next one, let's see if this one will work as well. I'll let x go to 2 here, and nothing bad happens, and this is just 20. Same with this one. Let's give this a try. Let x go to 2 and see what happens. And 2 minus 3 is -1. 4 minus 8 is -4, plus 3 is also -1. And so no problems, the limit of that equation is also 1. One more easy one. We'll let x go to 2. And 8 minus 3 is 5. Let's let x go to 2 here. So we'll say 2 squared minus 5 times 2 plus 2, 2 minus 7. And this will be 4 minus 10 plus 2, -4. And 2 minus 7 is -5. And that equals 20. And let's put in this value here. -5 plus 5 over -5 plus 7. -5 plus 5 is 0, -5 plus 7 is 2, and that just equals 0. Now you might be thinking that this is way too easy and that there must be a catch. Some questions are this easy, and the reason we did so many easy ones is because that's the first thing that I want you to do. And then if there's a problem, use some strategies to work around that problem. But the first strategy is just see if the limit is there as the value of the equation already. Let's try this one. We'll let x go to 3, so we get 3 minus 3 in the numerator. And we get 3 squared minus 4 times 3 plus 3 in the denominator. So 3 minus 3 is 0, and 9 minus 12 plus 3 is also 0. Now I'll put that in quotations because we can't have that, and this does not work. So here's an example where we need to think of a different strategy to get around this problem. I can't tell where this is going if it's going anywhere. So let's think of the things that we know from previous courses. I would say we could probably factor this quite easily. Now I'm not going to let x approach 3 yet, so I need to write limit and show where that limit is going. Then I'll factor this. And in the denominator, it looks like x minus 3 and x minus 1. And you see that this was a point of discontinuity. We can remove it. And now we can let x go to 3. So remember that when I cross this out, it's now 1. We'll write that. It's not 0. So it's now 1 over 3 minus 1, and that equals 1/2. So here's another one that we see is going to be a problem. If I let x approach 3 and I put 3 here, I'm going to get 3 minus 3, and that'll be 0. And I can't have 0 in the denominator. But this looks like a good candidate to factor. So I need to write the limit because I'm not going to let x approach 3 yet. It's not safe for that to happen. I'll factor this. X minus 3, x plus 3. And in the denominator, I have x minus 3 still. And we see that this was a point of discontinuity, so I can remove that. And now it's safe to let x go to 3. So I'll just say 3 plus 3. I've let x go to 3, so I don't need this limit anymore. And I can just get the limiting value is 6. Let's try the next one. Now I'm glancing at this one here, and I see if I let x go to 2, I'm going to get 2 squared, which is 4 minus 4, and that's 0 in the denominator again. So I can't have that. But this doesn't look like a good candidate to factor. I can factor the denominator, no problem, but this numerator doesn't look very nice. So I need to think of what other tools do I know when I'm working with radicals. And hopefully you remember something we did before when we were trying to rationalize the numerator or the denominator. And that would be by multiplying by the conjugate. So x plus this radical in the numerator and in the denominator. Now that looks like we just made the whole situation worse, but just hang on. Now I have to write the limit as x approaches 2 until I use that up. So here we have x squared, and then I get minus, and now I can just take this. I'll leave it in brackets just so we don't get mixed up with distributing in the negative. Now in the denominator, I'm not going to multiply these in. We'll just leave them separate for now, but I will factor the denominator here, because I always want to keep the denominator factored to see if I can cancel stuff out. So this one factored will be x minus 2, x plus 2, and then this big mess here, x plus root 3x minus 2. Okay, let's clean up the numerator. We got something we can factor here. So the limit as x approaches 2, this is x squared minus 3x plus 2. And all this in the denominator will still be here, waiting patiently. And let's factor this now. The limit as x approaches 2, x minus 2 and x minus 1. And that's very fortunate, because you see we can now cancel out the problem. The problem was this x minus 2 factor here wasn't letting us put in x equals 2. So once we remove that, it should be safe now to let x go to 2. So 2 minus 1 in the numerator, and in the denominator 2 plus 2, and 2 plus root 3 times 2 minus 2. Okay, so in the numerator we have 1. In the denominator, the first factor here is 4. And then the second here is 3 times 2 is 6, minus 2 is 4, square root of 4 is 2, 2 plus 2 is 4 again. And so our limit is 1 over 16. So far we've done 2 strategies, factoring and multiplying by the conjugate. This one's very difficult to see without visualizing where it's going, but if we look at x equals 1, we're going to get a 0 in the denominator, so that can't happen. Now we also see that we can't factor the numerator, and also multiplying by a conjugate won't help either in this case. So let's visualize using the strategies that we know what's going on with this graph. Now, we know that there is a vertical asymptote here at x equals 1 because it's an unmatched factor in the denominator. Also, we know that since we can't factor the numerator, then there's no x-intercepts. And also we know from dividing polynomials, if we divide a quadratic by a linear, we're going to end up with a linear. And it's got a positive slope, so actually, the overall shape of this is a linear. And this graph actually does this and this. And you could confirm this using some test values, but that's how it's looking. So as we try to approach 1 from both sides, we're going 2 different ways. So this limit does not exist. Here's another one where if I let x go to 0, there's going to be a 0 in the denominator. That's a problem. Thinking of the strategies I know so far, factoring and multiplying by the conjugate, I'm not going to be able to do either of those Just be careful on giving up too quickly. So if students find a question difficult, often they'll just assume that it doesn't exist. But go through all of the strategies and make sure that that is actually the case. Now, let's look at this one here. If we graphed it, it would have no x-intercepts, and it would have a vertical asymptote at x equals 0. And because it's squared, both sides will be positive. Now, in this case, as we approach 0 from the left and from the right, the graph is heading up to infinity. Now, I'm going to actually include that information. Although infinity is not actually a number, so there's no limit to this. So I must conclude DNE. I like to add this bit of information in here because it's going to come in useful later when we're doing curve sketching. So infinity is not actually a number. The next one looks pretty fun. Pause the video and give it a try, see if you can find the limit. Now hopefully you realized that we could just plug 3 in here. So 3 cubed is 27 minus 8 is 19. And 3 squared is 9, minus 9 is 0, plus 2 is just 2. But chances are, after you've done these questions, you might start thinking of factoring. This looks so fun to factor too. I mean, here we've got a difference of perfect cubes, and here we've got a quadratic. To factor the difference of perfect cubes, we take the cubed root of this term here, which will be x, and the cubed root of this term here, which will be 2. Now we square it here, and we multiply it together here, and square it here. And then you can remember using SOAP, same sign, opposite sign, always positive. So that would be factoring the difference of perfect cubes. In the denominator, we'd get x minus 1 and x minus 2. And you see we can actually cancel these out, but really that doesn't do anything for us. Our non-permissible values are 1 and 2, and so they have nothing to do with 3. But it was fun to factor it anyways. For this question, we want the limit of this as x approaches 1. And if I put in 1, I just get 1 minus 1 here in the denominator. That's 0, so that can't happen. So this isn't one of those easy questions. Yeah, too bad. Let's first get rid of the fraction within the numerator by multiplying the numerator and the denominator by the square root of x. And in the numerator, I'm going to multiply it in here. Now I need to write the limit as x approaches 1 because I haven't let x approach 1 yet. In here I got 1 minus root x, and in the denominator I do not multiply these in. I want to keep this as factored as possible. Now I'm looking at this limit as x approaches 1. I'm looking at this, and this could be a factor of this if I just do some tricks here. So the first thing I'm going to do is factor out a negative from the numerator. So then it becomes positive root x minus 1. And it will become clear in a second why I'm doing that. Next, I'm going to factor this. Now you might think that this is already factored, and in previous courses we would have considered this to be factored. But I can actually treat this as a difference of perfect squares. So this would be root x minus 1 and root x plus 1. And then I have a root x at the end. And now you see that I have a matching factor, numerator and denominator. And it's actually safe to let x go to 1 now because I've eliminated the problem. So in the numerator, I just have negative 1. Remember, when I divide, I get 1. I don't get 0. So negative 1. And I put in x equals 1 right here. So the square root of 1 is 1. 1 plus 1 is 2. And the square root of 1 is 1. So that's it. The limit is negative 1/2. Now, right about here, if you didn't think of factoring this, you can also multiply by the conjugate, and that will also work. After this, you should be able to find the limit of a function from its graph or equation. Here's some questions from the textbook. Give them a try. See if you know what you are doing.